Right now, beneath the calm blue waters off the coast of Indonesia, 16 megathrust segments are locked, and scientists say every single one of them is overdue. We are not talking about a regular earthquake. We are talking about a cascading rupture so massive, it could trigger a magnitude 9.0 or higher, bigger than the disaster that killed 230,000 people in 2004. And that event? Scientists now believe that was just a fraction of what this fault is capable of. 240 million people live in the shadow of what could be the most destructive geological event in modern human history. Cities with millions of residents, coastal villages with no escape routes, and a tsunami that would arrive before most people even knew the ground had moved. But here is what makes this truly terrifying. Scientists have identified something inside these locked segments, a hidden pattern that suggests the next rupture will not stop at one. It could trigger a chain reaction no warning system on Earth is fast enough to stop. So the question is not if the sleeping giant wakes. The question is, when it does, will 240 million people have anywhere to run? To understand why scientists are losing sleep over Indonesia, you first have to understand what is buried beneath the ocean floor. Not a single crack in the earth, not a localized weak point. What lies beneath the Indian Ocean off the coast of Indonesia is a geological monster of almost incomprehensible scale. It is called the Sunda MEGATHRUST, and it is one of the most dangerous fault systems ever identified on this planet. The mechanics begin deep beneath the seafloor, where two of Earth's great tectonic plates are locked in a slow, violent collision that has been ongoing for millions of years. The Indo-Australian plate, dense and heavy, is being driven beneath the lighter Eurasian plate in a process geologists call subduction. The heavier oceanic lithosphere grinds downward at a rate of roughly 50 to 70 millimeters per year. That may sound insignificant. It is not. Over decades, over centuries, that relentless grinding builds stress along the fault interface, the way pressure builds inside a compressed spring. The energy does not dissipate. It accumulates. It waits. The fault itself stretches more than 5,500 kilometers along the seafloor, running from the Andaman Islands in the Bay of Bengal down the western coast of Sumatra and Java, and continuing southeast toward the lesser Sunda Islands. To put that scale in perspective, that is roughly the distance from New York to Los Angeles and back again. It is one of the longest active subduction zones on Earth, and every kilometer of it represents stored geological fury that has not yet been released. What makes the Sunda megathrust uniquely terrifying compared to other major fault systems is the direction of its movement. California's San Andreas Fault, for example, operates through horizontal motion. Two plates sliding past each other sideways. Destructive, yes. But the Sunda megathrust moves vertically. One plate thrusts beneath another, and when it ruptures, it does not just shake the ground. It physically displaces the seafloor. Columns of ocean water hundreds of meters deep are violently shoved upward in seconds. That displaced water has to go somewhere. It goes toward the coast at speeds approaching 800 kilometers per hour, as a tsunami. This is the fundamental reason why subduction zone earthquakes are in a different category of catastrophe from almost any other geological event. The earthquake is only the beginning. The ocean itself becomes the weapon. But here is what makes the current situation more alarming than anything scientists have faced before. The Sunda megathrust is not a single threat waiting to rupture in one place. Researchers have now identified 16 distinct locked segments along this fault, each one storing its own independent reservoir of catastrophic energy. 16 separate triggers, 16 separate disasters, and any one of them could set off the rest. To understand what the Sunda megathrust is truly capable of, you do not need to consult computer models or peer through scientific projections. You only need to look at what it has already done once. December 26, 2004, the day after Christmas. At 7:58 in the morning local time, a section of the megathrust off the northern coast of Sumatra ruptured without warning. The earthquake measured between magnitude 9.1 and 9.3, making it one of the most powerful seismic events ever recorded in human history. The rupture tore along approximately 1,300 kilometers of the fault. The seafloor shifted by as much as 20 meters in some locations. The entire planet rang like a bell. Seismometers in Europe detected the tremor. Scientists calculated that the energy released was equivalent to approximately 550 million times the atomic bomb dropped on Hiroshima. Within minutes, the displaced seafloor launched a tsunami in every direction across the Indian Ocean. Waves traveled at speeds approaching 800 kilometers per hour, roughly the cruising speed of a commercial aircraft. Communities along the coastlines of Indonesia, Sri Lanka, India, and Thailand had no warning systems, no sirens, no alerts. Many had no idea what a tsunami even was. The water arrived as a wall. In some locations, it reached heights of 30 meters. In others, it traveled kilometers inland, erasing fishing villages, resort towns, and entire coastal communities in minutes. When the death toll was finally counted, more than 230,000 people were dead across 14 countries. It remains one of the deadliest natural disasters in recorded human history. The scale of destruction forced governments and international organizations to fundamentally rethink how the world monitors and responds to seismic threats across the Indian Ocean basin. But here is what the scientific community understood almost immediately, and what the public largely did not. The 2004 rupture, as catastrophic as it was, represented only a fraction of the Sunda megathrust. The section that broke that morning covered a significant stretch of the fault off northern Sumatra. But the segments beneath central and southern Sumatra, beneath Java, beneath Bali, they did not rupture. They absorbed the shockwave and held. They remain locked today, still storing centuries of accumulated energy with nowhere to go. Scientists did not breathe a collective sigh of relief after 2004. They leaned forward in alarm, because what the data revealed was not that the worst had happened. What it revealed was that the fault had only partially shown its hand. The 2004 disaster was not the defining event of the Sunda megathrust. For 16 locked segments still coiled silently beneath the Indian Ocean floor, it may have been nothing more than a preview of what is still to come. Not all fault segments behave the same way. Some sections of a megathrust slowly creep, releasing stress gradually through minor tremors and microseismic activity that barely registers on the surface. But others lock completely. The two plates grip each other with enormous friction, refusing to slip, forcing all of that convergent energy into storage. Scientists call these locked segments. And along the Sunda megathrust, researchers have now identified 16 of them, each one holding centuries of accumulated strain with no release in sight. The most critically stressed is the Mentawai segment, located off the western coast of Sumatra, near the city of Padang. Paleoseismic studies, which read the geological record of past earthquakes preserved in sediment layers and coral formations, indicate that this segment last ruptured in the 18th century. That means more than 300 years of continuous plate convergence has been absorbed and stored with no significant release. 3 centuries of a 50 to 70 millimeter annual collision, locked into a fault interface that has not moved. The pressure is staggering. Modeling studies suggest the Mentawai segment alone is capable of generating an earthquake in the magnitude 8.5 to 9.0 range when it finally breaks. Further south, the segments beneath Java and Bali present a different but equally alarming problem. These zones have not produced a megaquake in recorded history, which means scientists lack the historical baseline that helps estimate rupture cycles. Recent GPS measurements and seismic tomography data confirm that stress is actively accumulating across these zones. But thick sediment layers along the Java Trench are masking smaller seismic events, complicating risk assessment precisely where the stakes are highest. And then there is the cascading scenario, the event that keeps geologists awake at night. In 2004, multiple adjacent segments ruptured in sequence, each failure loading stress onto the next zone and triggering a chain reaction along the fault. If that pattern were to repeat across several of the 16 currently locked segments simultaneously, the resulting earthquake would not simply be large. It would exceed magnitude 9.0. Not a single segment of this fault is safe from that chain. A cascading rupture does not announce itself. There is no slow buildup, no warning tremor that politely signals what is coming. One segment fails. The stress it has been carrying transfers instantaneously to the adjacent locked zone. That zone, already at its limit, breaks. Then the next. Then the next. A chain reaction propagating along hundreds of kilometers of fault in minutes. Each rupture amplifying the total energy release into a magnitude that the modern world has never directly confronted at this scale. The timeline that follows is merciless in its precision. Within seconds of the initial rupture, the seafloor displaces vertically across a vast area. The ocean above it reacts immediately. An enormous pulse of water energy radiates outward in every direction at speeds approaching 800 kilometers per hour. For communities sitting in the deep ocean path of that wave, there may be hours of warning. For communities sitting directly above the rupture zone, there is almost nothing. The city of Padang, home to nearly 1 million people, sits approximately 60 kilometers from the Mentawai segment. Scientists estimate tsunami waves could reach its coastline in under 30 minutes from the moment of rupture. 30 minutes to evacuate a coastal city of 1 million, in the middle of the night, with roads already gridlocked by panic. Japan's 2011 Tohoku earthquake provides the closest modern reference point. A magnitude 9.0 rupture. Tsunami waves reaching 40 meters in height. Nearly 20,000 people killed, despite Japan possessing some of the most advanced seismic infrastructure and public preparedness programs on Earth. The Fukushima nuclear disaster followed, adding a cascading industrial catastrophe on top of the primary destruction. Japan was as prepared as any nation on the planet, and it was nearly overwhelmed. Indonesia is not Japan. The infrastructure gap is vast. Building codes in coastal communities are inconsistently enforced. Evacuation routes are inadequate. Public preparedness varies enormously between urban centers and rural coastlines. If a nation of Japan's capability was brought to its knees by a magnitude 9.0, the question for Indonesia is not whether the damage would be worse. The question is how much worse. And the answer, by every scientific measure available, is catastrophically so. Numbers at this scale have a way of becoming abstract. 240 million people. The figure appears in scientific risk assessments and government briefings, and it is easy to read it as a statistic, process it as data, and move on. But behind that number are fishing families on the western coast of Sumatra who have lived within sight of the ocean for generations. Farmers in the lowland plains of Java, whose entire livelihoods sit meters above sea level. Children in coastal schools in Padang and Banda Aceh, who practice earthquake drills without fully understanding what the ocean is capable of doing to their neighborhoods in under half an hour. The population exposure along Indonesia's western coastlines is unlike almost anywhere else on Earth for a fault of this type. Jakarta, a megacity of more than 10 million people, sits on the northern coast of Java. Bandung, Surabaya, Padang, cities of millions, are distributed across the precise geography that a cascading megathrust rupture would target with maximum force. The vast majority of structures in these cities were not engineered to survive a magnitude 9.0 earthquake. Many were built with no seismic consideration at all. The shaking alone, before a single wave arrives, would collapse buildings across entire urban districts. Then the water comes, and after the water, The secondary disasters follow in sequence. Landslides triggered across destabilized hillsides, dams compromised by the initial shaking, sending floodwaters into already devastated valleys. Industrial facilities breached, releasing chemicals into water supplies. Disease spreading through displacement camps where hundreds of thousands of survivors compete for clean water and medical attention. Each catastrophe feeding the next in a chain that emergency systems, even functioning ones, would struggle to contain. The displacement would not be temporary. Communities built on coastlines that no longer exist cannot simply return. Agricultural land salted by seawater intrusion cannot produce food for seasons. The economic destruction rippling through families, through villages, through entire provinces would reshape the human geography of the region for a generation. 240 million people. That is not a statistic. That is a civilization standing directly in the path of a geological event that the science tells us is not a possibility. It is a certainty. The scientific community has not been standing still. In the 2 decades since 2004, exposed the catastrophic gap in regional preparedness. Indonesia and its international partners have invested significantly in understanding and monitoring the Sunda megathrust. The Indonesian Agency for Meteorology, Climatology, and Geophysics, known as BMKG, now operates an extensive network of seismic stations, tide gauges, and GPS sensors positioned across the archipelago. These instruments feed continuous data into detection models designed to identify tsunami-generating earthquakes and trigger public warnings within minutes of a rupture event. The Indian Ocean. Tsunami Warning System, built largely in response to the 2004 disaster, represents a genuine and substantial leap forward in regional preparedness. But the warning system has a problem that no amount of technology has yet solved. For communities located closest to the fault, the warning may arrive after the wave already has. The physics are unforgiving. When the Mentawai segment ruptures, the tsunami it generates does not cross an ocean before reaching land. It travels 60 kilometers. At 800 kilometers per hour, that journey takes approximately 4.5 minutes. Even with a perfectly functioning detection and alert system, communities on the western coast of Sumatra may receive warnings with 20 to 30 minutes before impact at best. Evacuating dense coastal populations in that window across road networks that will already be damaged by the initial earthquake shaking is a problem that sirens alone cannot solve. It requires roads built with evacuation in mind, vertical shelter structures that populations can reach on foot in minutes, and years of community education that transforms the instinct to watch the ocean into the instinct to run from it. Scientists are pushing the boundaries of what monitoring can achieve. Ocean bottom seismometers deployed along the fault provide data from directly above the rupture zone. Offshore drilling projects extract sediment cores that extend the paleoseismic record back thousands of years. Satellite geodesy tracks millimeter-level ground deformation that signals where stress is accumulating fastest. The understanding of the Sunda megathrust improves with every passing year. But the fault does not pause while the science catches up. It has never once waited for humanity to be ready. It is tempting to frame the Sunda megathrust as Indonesia's problem, a regional catastrophe contained within the borders of one archipelago nation, devastating to those directly in its path, but ultimately distant from the rest of the world's daily concerns. That framing is not just incomplete, it is dangerously wrong. Indonesia is Southeast Asia's largest economy. Its ports, its manufacturing corridors, its agricultural output, and its energy infrastructure form a critical backbone of regional and global trade networks. The Strait of Malacca, one of the busiest and most strategically vital shipping lanes on Earth, sits within the direct sphere of influence of a Sunda megathrust rupture event. Approximately 40% of global trade passes through that corridor annually. A megaquake striking Java or Sumatra would not merely destroy Indonesian infrastructure. It would send shockwaves through supply chains that stretch from East Asia to Europe to North America, disrupting the movement of goods that the global economy depends on, with a completeness that no boardroom contingency plan has fully accounted for. The cascading industrial disasters would compound the economic paralysis. Coastal manufacturing facilities breached by tsunami inundation. Chemical plants releasing toxic loads into waterways that serve millions. The Tohoku earthquake in Japan demonstrated with devastating clarity how a single seismic event can trigger a nuclear crisis that contaminates land and ocean for decades. Indonesia's industrial coastlines carry their own version of that risk, and the regulatory and containment infrastructure to manage it under catastrophic conditions is significantly less robust than what Japan had in place in 2011. Financial markets would absorb the impact almost immediately. Insurance claims from a megaquake and tsunami striking densely populated Indonesian coastlines would generate losses that dwarf the reserves of regional insurers. Global reinsurance markets would face pressures not seen since the largest catastrophe events of the last century. The economic destabilization would radiate outward through currency markets, commodity prices, and sovereign debt across a region that is already navigating significant geopolitical tensions. The humanitarian response required would stretch international coordination to its absolute limits. The 2004 disaster mobilized a global relief effort that was, by every historical measure, unprecedented in scale. A magnitude 9.0 or greater event striking the same region with far greater population exposure would require a response that makes 2004 look manageable. Aid organizations, military logistics networks, and international relief agencies would be simultaneously overwhelmed and underfunded. This is the reality that the Sunda MEGATHRUST forces the world to confront. Not a local tragedy that the global community can observe from a distance and respond to generously after the fact. A single rupture event along 16 locked segments could reshape the economic, humanitarian, and geopolitical architecture of an entire hemisphere. The fault sits beneath Indonesia, but what it unleashes will belong to all of us. Stand at the edge of the Indian Ocean on any given morning, and the water is beautiful, turquoise and vast and indifferent, stretching to a horizon that gives no indication of what lies beneath it. The same ocean that draws tourists to Bali's beaches and sustains the fishing communities of Western Sumatra with generations of livelihood. The same ocean that on December 26, 2004, became a wall of water that killed more than 230,000 people before most of them had finished their morning coffee. The ocean does not change its appearance based on what is building beneath it. It looked exactly the same the morning before 2004 as it did the morning after. That is the nature of the threat that 16 locked segments of the Sunda megathrust represent. Not a visible danger, not a slow deterioration that provides years of warning and gradual adaptation. A silence that has been building for centuries, accumulating energy with every passing year, indifferent to the cities and families and civilizations that have arranged themselves directly in its path. The science is unambiguous on the fundamental question. The locked segments will rupture. The energy stored along the Mentawai segment, along the fault zones beneath Java and Bali, along every one of those 16 pressure points, will eventually be released. The only variable that science cannot resolve is timing. Not if. Not whether the threat is real, only when. And the honest answer from every researcher who has studied this fault with rigor and integrity is that it could be tomorrow, or it could be a century from now, and there is currently no instrument on Earth that can tell the difference. What humanity can control is the state of readiness it achieves before that moment arrives. Early warning infrastructure that reaches the last fishing village on the most exposed coastline. Evacuation routes engineered for the speed that near-field tsunamis demand. Buildings designed to survive the shaking that precedes the wave. Community education so deeply embedded that the instinct to run from the ocean becomes as automatic as breathing. International cooperation frameworks capable of mobilizing a humanitarian response at a scale the world has never yet been asked to deliver. The 2004 disaster forced a reckoning. It revealed how catastrophically unprepared the world was for what the Sunda megathrust could do. The question that the 16 remaining locked segments now place before every government, every scientist, every international institution, and every coastal community within reach of this fault is whether that reckoning produced enough change, whether the lessons were learned deeply enough, whether the preparation that followed was proportional to the threat that remains. The sleeping giant has not woken, but it has never stopped waiting. And the only question that matters now is whether we will be ready when it does.